Theory of viscosity of liquids. This theory was proposed by Eyring. We know that in a pure liquid at rest, the individual molecules will be in constant motion. So here Eyring proposed the cage-like structure of molecules. He suggested that under stationary state or a fluid or a liquid at rest, due to the close packing of molecules, the motion is confined to the vibration of each molecule within a cage formed by its nearest neighbor. He proposed the cage-like structure for molecules. And under this stationary state, the molecules undergo rearrangement continuously, in which one molecule at a time escapes from its cage into an adjoining position that is called as the hole. So we can see this figure. So this is the figure given. So these are the molecules arranged in layers A, B and C. As shown here, this is molecule 1 and this molecule 1 will be escaping into its adjoining position. Here we are having a hole. It will be escaping into its nearest adjoining position hole, and this molecules undergo continuous rearrangement. So we can represent this energy as we are having an energy barrier delta G0 by N. So these molecules have to jump at a distance A at a frequency K per molecule. Frequency I am representing it as small letter k, and the frequency of this jumps is represented as K is equal to Kt by h e raised to minus delta G0 by RT. Here the capital letter K corresponds to Boltzmann constant and this h corresponds to Planck's constant, and R is universal gas constant. And when the fluid flows under the application of a force in the x direction with a velocity gradient dvx by dy, the frequency of molecular rearrangement increases. This molar free energy is represented by minus delta G is equal to minus delta G0 plus or minus A by delta tau yx V by 2. This delta G is the molar free energy under the application of force. A by delta into tau yx V by 2. It is the conditional work done on molecules to make a move. So here we are not going into the derivation of these equations, just study these equations. And the frequency of forward jump. So if the molecule is having a forward jump, we can represent the frequency as Kf is equal to Kt by h into e raised to minus delta G by RT. So when substituting the values of delta G here, you have to use positive sign for forward jump and negative sign for backward jump. So we can see it. Kf is equal to Kt by h e raised to minus delta G0 by RT into e raised to A into tau yx V by 2 delta RT. So this is equation number 3. So similarly substitute for backward jump also. Here we are using negative sign for backward jump. So that is equation number 4. Next is the velocity profile Vxa. It is the velocity for layer A, and Vxb, it is the velocity for layer B. So the net velocity, that is Vxa minus Vxb, it will be equal to A into Kf minus Kb. That is, A is the distance travelled per jump and Kf minus Kb is the net frequency of forward jump. So the velocity gradient we can find out by dividing it with a delta term. So you will get A by delta into Kf minus Kb. So velocity gradient, we are representing it as dvx minus dvx by dy. Here the flow direction is in the x direction, that is why we are taking it as Vx. Then after substituting equations 3 and 4 and 5, we get this equation, A by delta into Kt by h e raised to minus delta G0 by RT into e raised to A into tau yx v by 2 delta RT minus Kt by h e raised to minus delta G0 by RT into e raised to minus A into tau yx v by 2 delta RT. So we can solve that equation. We know the relation e raised to x minus e raised to minus x by 2. It will be equal to sine of hx. So we are using that equation here and solve it. First take Kt by h into e raised to minus delta G0 by RT common. Then solve this portion. Then if A into tau yx v by 2 delta RT is very less than 1, then we can write sine h of A into tau yx v by 2 delta RT is equal to A into tau yx v by 2 delta RT. So use this in equation for velocity gradient. So using this we get A by delta Kt by h e raised to minus delta G0 by RT into A into tau yx v by delta RT. So solve that equations. So finally we get this one. And if A is approximately equal to delta, and rearrange this equation in the form of tau yx. So you get r by k into h by v e raised to minus delta G0 by RT minus dvx by dy. This r by, we know the relation, r by n is equal to k. That is, here this k is Boltzmann constant, r is gas constant and n is Avogadro number. So use this relation here. So you get the expression for tau yx as minus nh by v e raised to minus delta G0 by RT into dvx by dy. That is equation number 6. And for Newtonian fluid, Newton's law of viscosity is applicable. Tau yx is equal to minus mu into dvx by dy. So you compare these two equations 6 and 7, you get mu is equal to nh by v e raised to minus delta G0 by RT. And the value of delta G0 we can write as 0.408 into delta U vaporization. That is, the free energy of activation is related to internal energy of vaporization at normal boiling point by this relation. So you can substitute this 9 in 8. And also the energy of vaporization at the normal boiling point can be estimated from Trotton's rule. So Trotton's rule is delta U of vaporization is approximately equal to delta H vaporization minus RTB. That is approximately equal to 9.4 RTB. So substituting 9 and 10 in equation number 8, you will get mu as NH by V e raised to 3.83 TB by T. So, these equations equation 11 indicate an exponential decrease in viscosity with temperature. So it agrees with the observed behavior of most of the liquids. And also these equations are not very much accurate. We can expect a error of about 30% while using this equation. So this is the equation for getting the viscosity of liquids. So based on this viscosity of liquids, a problem is given as classwork in ET lab. So do it and submit it.